Hi, I'm Tina Carbrello, and it's my great pleasure to introduce the next installment of our NAMS webinar series. Here to present on sustainability and scale-up in membranes is Isabel Escobar.
Thank you so much, Tina. Thank you for inviting me to give this webinar. Like Tina said, I'm Isabel Escobar. I'm a professor at the University of Kentucky, and I'm going to present some work that we have been doing for about a decade on the scale up of membranes made using green solvents. This is a collaboration that has been going on for about a decade with Professor Tequila Harris from Georgia Tech, and a new collaboration with Dr. Diana Byrne from the University of Kentucky, looking at sustainability, life cycle assessment, and what is next for this kind of work. So with that, I would like to start with a trip that I took to Imagine Membranes a couple of years ago. And we were taken in one of the trips to a tea farm. And this tea farm sells tea throughout the world. They're world renowned for the high quality of their tea. And it's a very organic, and they take a lot of pride in their organic tea. And to keep it organic, to keep it high quality, they don't want to put pesticides. They don't want to do anything that could impact the flavor and obviously make it not organic. So they determined that goats from a nearby farm would love to eat the weeds, but absolutely would hate the flavor of the tea. And that made an impact on me because that is the meaning of sustainability, of something that's sustainable. The tea farmer is happy because they don't have to use pesticides. They're able to say it's an organic farm. Their tea tastes great. The whole world's willing to pay a great deal of money for this wonderful tea. The goats are happy because they have food and they're eating the weeds and they have absolutely zero desire to touch the tea. The owners of the goats are happy because they don't have to buy food. And those of us who drink the tea are happy because we're drinking an organic tea and we know it's sustainable. So I think in the end, that's really the meaning of it. Everyone involved in the process is happy. So this is what we try to achieve in our work. And obviously, we are membrane scientists. We know how a membrane is made, but I will go through how we focus. We focus primarily on non-solvent induced phase separation, or NIPS. Obviously, there are a number of different ones. There is TIPS with the temperature induced. There's IPS with the evaporation. There are interfacial polymerization. There are a number of other ways. We primarily focus on NIPS because it's versatile, it's easy to make, and it can, and we have a lot of control over the membrane. So in order to do this, in order to make membranes using NIPS, we take the polymer, we dissolve it in the solvent to make the dope solution. That's pretty standard. We then spread that dope solution on a substrate. We move a glass plate, a Dr. blade over it. It evaporates over time. Then we put it in the non-solvent bath, and then we have the membrane. There it is. And here's an image of David. This is David Blue's hands making the membrane. I forgot to say in the introduction that he recently defended his dissertation. He defended on February 27 of 2025. And here he is just demonstrating the NIPS process, how the organic solvent leaves the matrix, the dope matrix, and it goes to the non-solvent bath, that's water, and now the waste is that organic solvent in the water bath. So again, we use NIPS because it's versatile, it gives us a lot of power over chemistry, and it gives us a lot of power to tune the membrane performance. In this, we have the polymer and solvent. We can put a substrate under, a polymer support or make it a freestanding membrane. We can tune the evaporation time. We can use a combination of polymers and solvents in order to increase or decrease the precipitation time and make our pores more sponge-like or more finger-like, all in the choice of polymer and solvent and in how fast the phase inversion occurs. So this, again, gives NIPS a lot of power. On the flip side, we have the drawbacks of NIPS. And the drawback is primarily we now have as the waste the solution that's made of organic solvent in water. And back in 2015, a survey was done and published of what is done, how that organic solvent concentration in the water bath is addressed. And it was found that really there's a lot of just sending it down the drain if the amounts are allowed to be sent down the drain, paying fines to do it, contracting a company to take it and treat it in-house if the producer is too large, or dilution. And dilution is not the solution. That's one of the things that I love to say here. Dilution is not the solution. We do not want that to go down the drain. But since about early 2010s, I've been particularly following rules that have been happening, what has been happening worldwide, especially with the use of solvents for the fabrication of membranes. And in the REACH authorization in Europe, a lot of organic solvents were either banned or they were listed, as in their use is not ideal and it should be avoided. And then following, the US EPA also started regulating toxic substances. So now there's a much greater look into the use of these organic solvents because of their toxicity. And that was one of the drivers when I moved to the University of Kentucky to start focusing a lot more of my work towards green solvents, towards trying to make the membranes with similar characteristics as those with the traditional solvents, but using the green solvents. So again, we have the conventional solvents. And these conventional solvents like DMAF, DMF, NMP, etc. There's a long list of them, and they are flammable, they're volatile, they're toxic, non-biodegradable, non-renewable. They have just a heck of a lot of characteristics. They're not desired. They're not desired to be in the wastewater, not desired to be in a receiving water, and are just not desired for operators, for engineers, for students, for anyone to work with them. So we have focused a lot on replacing them with green solvents. Green solvents are primarily defined as those that would have low volatility, low flammability, come from renewable sources, are biodegradable, have a lower toxicity. And here we have some of the most famous ones like Polar Clean, GVL, Cyrene, ethyl acetate, but there are others. This is just a short list of them. The work on green solvents has been very quickly increasing throughout the world, which, by the way, makes me very happy. Okay, so we start with doing the relative energy difference calculations. We use Hansen solubility parameters to first screen. This is our number one. We screen out, we take the polymer that we want, and we just look at a variety of different green solvents. Is it even worth to go down the path of looking at this solvent, or is it a waste of time because it absolutely, there's no way it would ever dissolve. They're not compatible. And in the RED calculations, what we have in the Hansen solubility is a combination of dispersive forces, polar forces, and hydrogen bonding, and how those interact between the polymer and the solvent. And I have a little schematic on the next slide, but I want to start with some limitations of this. For the selection, it is a great first selection. It is a great process to weed out those that absolutely are not compatible. But parameters can vary with temperature. It oversimplifies the entire calculation. And the size of the molecules can also play an impact on how this, on the values. The assumption is made for RED that the polymer is this perfect sphere. And so in this perfect sphere, a good solvent with a relative energy difference less than 1 is one that right here, it can penetrate this perfect sphere. Excuse me. A bad solvent is one that cannot penetrate. So when we do the relative energy difference, which is the RA divided by the R naught, with the RA being the Hansen solubility distance to the polymer interaction, as shown here, the Hansen solubility and the polymer interaction, we see if that ratio is greater than 1, there is no way that that solvent could ever enter that sphere. And so it is considered an incompatible solvent for that polymer. On the flip side, for those that look at polymer, at solvent separation, so polymers or membranes that would be resistant to solvents, they would be looking at the opposite. If the RED is higher than 1, we can definitely use the solvent in the separations and it will not dissolve the polymer at all. So this can be looked at both ways for those that are making membranes for solvent separations and those of us that are trying to make green membranes. So through the initial screening, we screened a heck of a lot of them, and we found that Polar Clean and GVL were the ones that had the potential to dissolve polysulfone, which obviously we went with polysulfone. That's one of the workhorses in the membrane world. It's an incredibly cheap, powerful polymer. We all love polysulfone. And from an academic standpoint, there are so many publications with polysulfone, we can always validate our work. So we like Polar Clean a lot because it's a chemical valorization. It's a byproduct during the production of nylon 6,6. And so the expected sustainability of that is significant. When we started working with this, our thought was that Polar Clean would be the absolute most sustainable one because of the chemical valorization. GVL, on the other hand, is a biodegradable, comes from that, from biomass, from cellulose, hemicellulose, and that process. So our hypothesis here was that Polar Clean and GVL would be analogous to traditional solvents in order to make membranes. Now, we published a lot on this. Zhao Baodong, who is chairing NAMS 2025, did a lot of work showing that structure-wise, there were similarities between Polar Clean and DMAC, between GVL and NMP, and there were some characteristics that were similar. And because those RED values were less than 1, there was promise in those for their use to make polysulfone membranes. Some characteristics of them, as you can tell, they are larger molecules. Their density is approximately the same. Their viscosity is higher. And that is something that from just a purely chemical engineering membrane making lab, I didn't care at all to start with. But through my collaborations with Professor Harris, it became progressively more important that this viscosity is really a significant impact on the making of the membranes. So as the first step, we usually we do the RED values, and then we go into the thermodynamics, and we do our triphase diagrams. I am not going to go through all of the thermodynamics of this. As much fun as it would be to go through all of the thermodynamics of this, we just want to look at some very specific similarities. For the first one here, we looked at just Polar Clean, polysulfone, and water, and we saw that Polar Clean and DMAC pretty much followed the same lines and behaved very similarly in those cloud point curves in the thermodynamics development. Then through a lot of work, a lot of publications that we have done, we determined that ideally, in order to use GVL, as shown on this one, we had issues. There were a lot of issues with using GVL. And as we can see, especially down here in this lower side of the triphase diagram, as we are close here to this 100% water, 0% solvent, we see that the composition path, which is the distance between the axes and the midpoint of the cloud point curve here, is the shortest for the GVL, which means that it is the most thermodynamically stable, which means it's the least likely to be able to form a membrane. We would have to use a lot of water. And as you can see here, the percentage of water that we're adding is the highest. And we would still have issues in actually getting to form the membrane, to getting the GVL to leave the dope solution. So we determined that once we mixed Polar Clean and GVL, we actually were able to make membranes, and we had cloud points. And again, we had very similar operation as when we had just pure DMAC. So then moving on to the next phases, a lot of people are now looking at green solvents, which again makes us incredibly happy. There are groups throughout the world that are looking at green solvents. I know that this is a really busy plot. And we have here use of Polar Clean with a variety of different polymers, polysulfone, polyether sulfone, cellulose acetate. We have styrene, again, with a variety of polymers. We have GVL. We have here using cellulose now for the polymer, and so on. Green solvents, just a variety of green solvents. So it's a field that is growing, but is limited to the bench scale. It is very limited to those of us that I love to say a large scale membrane piece for me is this. This is where we are. This is when we talk large scale. And when I started collaborating with Professor Harris, we were talking about sending some initial samples to her for her to scale them up. And she said, well, how much can you send? And I was thinking 100 milliliters. That's a lot. That makes a lot of my samples that look this big. And I said, I don't know. How much do you need us to make? And her reply to me was 1 to 2 gallons would be great. And I had a nearly pass out moment, because making 1 or 2 gallons for me at my bench scale size would be just an incredible effort from my students, from materials, for everything that we do, for even the mixing of the dope. So over time, we got to where we were talking the same language. And recently, UVA published a collaborative paper on the Journal of Membrane Science that talks about one of the main hurdles of membranes and membrane development. And people like me live in this world right here. We make a new material, we make a membrane, we publish a lot, maybe we get a patent, we get a new grant, we make a new material, we make a new membrane. It can do all of these awesome, wonderful things. And trust me, I make a lot of these. I know how awesome we can make them. I add two-dimensional nanomaterials to them. I add all of these fun functionalities. I do the processes. There are 4, 5, 6 steps to the making of the membrane. The addition of something that would make this piece be worth $1,000. I do all of these, and it's an incredible amount of fun, and it provides the world with pure science and pure understanding of how materials behave when they're in contact with each other. But quite often, the desire for industry, it should be right here, is a process. So there's such a gap here. There's such a large valley in how do we take this awesome, fun, new material, new membrane, make a module out of it. So this, it felt like another motivation for the work that Professor Harris and I did, because we felt that the world was out there discussing the same issue as we were. And it is this valley right there. And it requires multidisciplinary collaborations because I absolutely don't have the knowledge for a scale up. I don't have the knowledge for a slot die casting that can take this piece to this piece that or larger. She can make as long as I can send her enough dope, she can make larger and larger pieces. So multidisciplinary collaborations like that are needed because, as we are going to discuss, there's a lot here that is absolutely not trivial and is incredibly difficult science. So that leads to the point of my discussion today, which is using polysulfone, polar clean, GVL, water, and electricity to making the dope, potentially heating the dope, and making some slot die coating. So again, this is our objective. We'll start out with characterizing the dope and looking at slot die fabrication at this, what you see here in the dark blue. This is the dope solution in becoming a membrane through NIPS. We did it either on the glass plate or on a support layer. And we compare that with doing the Dr. Blade in my lab, the slot die, and we compare NMP, DMAC, and the Polar Clean GVL solutions. So remember when I talked about the viscosity? Here comes the viscosity again. The viscosity significantly impacts the slot die casting. It impacts the processing because in the slot die, we have the dope in the syringe pump and it's pushing through the slot coater into this thin film. So it is not the manual Dr. Blade that we have the power over it, but it actually requires the ability for that dope to be able to have a flow rate. So we all know fluids and we all know all of those laws, and we know that the viscosity is going to have an impact. And we need to have limits within the viscosity because we need to have our dope solution to be a Newtonian fluid. As it starts to behave as a non-Newtonian fluid, NIPS will no longer work as NIPS, and we will start to have issues in making the membrane. That membrane will no longer have homogeneous properties throughout the membrane. So now looking at the slot die coating, these are prediction formulas. These are formulas that were developed in Tequila Harris's lab that relate the velocity right here of the substrate, which again can be glass or it can be a porous support, to the flow rate of the dope solution coming down, any pressure that is put here, and surface tension, and within the surface tension, we have the viscosity. And for every single dope solution, for every single combination of polymer and solvent, we have to develop a casting window. And this casting window is where we have perfect casting, where we're going to be able to develop a membrane that has homogeneous properties throughout the membrane, where every single piece of the membrane will provide the exact same permeability and rejection. When we are outside in this area where potentially our flow rate of the dope solution coming out is too high, there's going to be an accumulation back here of the dope solution, and it's called dripping. And now some of the NIPS, some evaporation starts here, and we're going to have a very inconsistent membrane, a very inconsistent separation selective layer at the top of the membrane. If the flow rate and the velocity of the substrate are too fast, we're going to have just a bunch of cracks throughout the membrane. And if we are over here in the bottom where the velocity is too high, but the flow rate of the dope is not high enough, we have some air entrapment. So we're going to have a lot of bubbles, very large bubbles within the membrane that could potentially explode or collapse during filtration. Another issue that we have when we're dealing with Dr. blade, we're dealing with a stainless steel Dr. blade. It is what it is. With a slot die coater, we can have glass, aluminum, or stainless steel for the coater itself, and all of those provide different contact angles with the polymer, with the dope solution. So those also impact the ability on how well that that dope comes out through the slot die and makes a membrane. And here we have a membrane made with an aluminum versus a membrane made with stainless steel. And hopefully you can see that there are some imperfections here on the side. There are some squiggly lines. There are more squiggly lines back here. And that's all because it is interacting. Just a 2-degree interaction leads to additional issues and additional interactions and problems. So we determined that the stainless steel was the optimal. And here's just a membrane being made at Professor Harris's lab. And so this is how we proceed. Now, when we have a new dope, when we have our dope with our green solvent, we have no historical data on how this is going to operate. So we have to develop a casting window by ourselves. And if we start out with trial and error, we can get to where we have dripping. So these are dope lines that are just not making a membrane, or we can get it to where it is a membrane, but it develops scratch lines, again, because our flow rate and our velocity are not matching correctly, and so they're not making a viable membrane. And we can make, again, just by making, here's an example of dripping, where the membrane is really not making, in the edges are not uniform. And as my student David loves to show this, we can make dozens, hundreds of bad membranes. We can waste gallons and gallons and gallons of dope solutions in attempting to determine what the casting window is for our green solvents. And any modification that we make, we now went from 17% polysulfone to 18%. We're potentially redoing the entire casting window. So it is labor intensive and is not effective. So Tequila's group developed a numerical modeling, and they're using Interfoam, which is within OpenFoam, and it's a manuscript that is out in press right now. It has just been accepted for publication, and it's a model of the slot die coder. So this here is a side view of the slot die coder, and this would be a top view of it to the model. And for modeling purposes, we're going with it. Our assumptions are a fully developed flow, so that we are no longer in that unsteady state region. We are gauge pressure of 0, so atmospheric conditions are 0, they're not impacting. We are at ground level. We have a no slip condition, static contact lines. You can see here all of our assumptions and boundary conditions associated to where we are. No slip on the walls. That means and this is a top view and this is the side view, again, the same. The dope is not attaching, it's not sticking to the walls. And so we can start using this. And I'll show a couple of the videos, though I might move around a little bit, but in this one, so this is again the side view. This is the slot die coder. This is the dope solution coming through the slot die. We can set a flow rate, we can set a casting speed, and we keep the coating gap at 0.2 millimeters here, and we look at the residual. The residual, we want it as tight as possible and as linear as possible during the simulation, because it means that those will be the perfect casting conditions. And if I move this here just a little bit, we can see that this case would lead to a perfect casting condition. We have the dope is moving at an appropriate flow rate over time. I'm not going to let the whole video play, but we don't have dripping in the back, and we're not moving so fast that this dope starts to have break lines here and significant air gaps. Okay, this is the second video, and the first thing that you can see here is how the residual is now a heck of a lot more erratic. So the residual is bumping a lot more, and this is because as we start our casting here in the simulation, we now see that potentially our flow rate is too high for the speed here of the substrate. And now we're starting to get an accumulation. The dope is starting to accumulate to the back. And soon we have the issue of dripping. So now the dope is accumulating here. That is not desirable. We're starting to have some evaporation of the solvent here, and now all of our conditions, we also have an accumulation here of the dope. So now the membrane will be incredibly uneven with terrible properties, and something that will not work in the end. And after making many of these, we can either do these by hand, and this part of our casting window was developed by hand here, and you can see we have a few data points. We have 8 data points. The top are the dripping effects. Again, the flow rate is too high, and we start to get unevenness at the edges of the membrane. The bottom is air entrapment. We start to have bubbles exploding within the membrane. And when we do it with the simulation, we were able to validate that simulation. So here, these are the experimental results. These are the open foam results that within the same range, they follow the same trend within the same standard error. And we were able to continue that casting window. So being able to use the validation, being able to use open foam shows that we can indeed simulate how the dope behaves within the slot coder. So then to continue on with this project, we wanted to also add a support layer to the membrane, because obviously, again, membranes have support layers. We love to make membranes without them. That way, they're just easier to make. But the actual casting on the support layer using the slot die coder and our Dr. Blade showed itself to be more complicated than we had expected. And that's primarily because these non-woven support layers, they have fairly wide gaps that the dope can penetrate through, and thus just leave these incredibly wide gaps, have having nips happen within the pores here, and it would just not make a membrane. It actually makes an incredible mess. And so the purpose of the work, and we published this last year on the Nature Portfolio Journal Clean Water, what we did was make a full comparison of Dr. Blade and slot die coating, and we made the membranes both on a glass support, and then we just put them on top of a support paper for filtration. We made them, we made them, and then we also put on top of the PET non-woven support, the Holitex, for filtration. Then we started casting directly on the support by casting just directly on that support, or in here for where we would make a very thin layer of dope on that support and then cast the full membrane on that support. And similarly, at the slot die coating level, what we did was spray. So we added a dope spray on the support in order to do the same as that thin pass layer. And we also compressed it and then added that spray coating as a pre-treatment step. And we looked at how well those were attached to the membranes. So how well the support and the membrane were attached to each other. And we went to some ASTM methods in order to determine the classification, in order to determine that attachment. And ASTM has a method that a grid is made on the membrane. This you can see here on the membrane. And this is what the grid looks like. And then it provides the details on how to attempt to scratch and pull it out. And then on observations, if none of it comes out, it is considered to be this 5B. If all of it comes out and there's absolute zero sticking to the that support, to the porous support, it's a 0B. And then there is everything else in between. And the first thing to notice is that the slot die made a better attachment. Now, in some of the cases, especially here with the Dr. blade, we were right there. There was very little sticking, actual sticking to the porous support, even though we did the pre-treatment. As you can see in both of these. With the slot die coater, we had some cases that had poor sticking, but right there, when we sprayed the dope solution as a pre-treatment on the porous support, we were actually able to get a good adhesion. To be in this 3B category here is not ideal yet. And maybe we need to increase the spraying time, but we were able to actually develop something that stayed attached. Now, in the way that we performed the tests, this was not a significant issue because we just performed them under pressure and then we did back flushing. But for a scale up, this does become an issue, and this does show that the slot die coating was effective. We looked at then starting some comparison between the Dr. blade and the slot die coating, and we looked at a variety of SCMs, both the surface as well as the cross section, and we were able to determine that the mean pore diameters for all of them were approximately the same, and they all had a sponge-like cross section. We did permeability using a couple of different solutions. We did a BSA solution because BSA, again, is very well known. There's a lot of data for BSA using polysulfone membranes. And what we found is that we started with a pre-compaction, and that pre-compaction was more needed for those membranes made at my scale, at the scale of the Dr. blade. When they were made with the slot die coater, that pure water filtration, that pre-compaction did not show as significant of a drop as it did with the Dr. blade. However, when we started the BSA filtration under pressure, all of them perform at approximately the same permeability, and all of them within error had high BSA rejection with the membrane, with the slot die coating membrane that was pre-treated with just the spray coating, showing the highest BSA rejection. We then used our second substrate, which was sodium alginate. This is primarily because it tends to stick more to the membrane. We again performed pre-compaction. We saw a little bit more variation on the permeability, but again, all of them showed pretty high permeability levels. Rejections were lower. Obviously, we chose sodium alginate because it's more of a foulant. It represents natural organic matter more, and it has a wider variety of sizes. And we had, as expected, a much wider variety of rejections, but that SDC3, that slot, that pre-treated slot decoder, did perform very well in both. So then we started thinking that we've made these great membranes. And our membranes, we are publishing a lot on the making of the membranes and how they perform with these green solvents. But what we have not touched much yet is their sustainability. How sustainable is really the making of these membranes, of these green membranes? And this is the new collaboration with Dr. Diana Burns from the University of Kentucky. And now what we're doing is, can we do a life cycle assessment on this? Now, obviously, there are a lot of boundaries to our life cycle assessment. We are looking at what is done at a small Dr. Blade scale and what is done at a slot decoder. We are not actually looking at a full scale life cycle assessment because there are a lot of parameters we don't have, and there's ultimate use and disposal. So we are looking at polysulfone and our solvents. We decided to compare with DMAC, NMP, and our Polar Clean GVL. The dope mixing that uses electricity. In order to make the dope, we have to do some heating of the dope and mixing. So we have some electricity here. During Dr. Blade, there is no electricity use because this is just student power. If I were to tell my students that they would have to be plugged in the power, there would be issues because there would be a significant safety concern. They're much more power like me by coffee rather than by electricity. But the slot decoder is powered by electricity. And in the NIPS, we obviously have water. Now, from back when I started the presentation, maybe about 35 to 40 minutes ago, I was talking about that viscosity of the polar clean. So now that viscosity is going to come back here as an issue in our life cycle assessment, primarily because we need more material. We need more material, especially during the NIPS process, in order to get to our steady state. So there is a use of more material for the polar clean. And for our fabrication techniques, I'm going to show you the 3 membranes that we made. We use PSF at the Dr. Blade level. We call them M1 with DMAC, 2 with NMP, 3 with our Polar Clean GVL, using slot decoders, and 4 through 6. Again, important to remember is that M3 and M6, those are the ones with the green solvents. And we looked at effects with respect to global warming, ecotoxicity, smog, acidification, eutrophication, fossil fuels, carcinogenic and non-carcinogenics, respiratory effects, and ozone depletion. And unfortunately, we were very surprised to find that M3 and M6 across the board showed higher negative impact as compared to the NMP and the DMAC when it came to the ones that we were looking at. Obviously, they're all shown here. And one of the issues is the viscosity. The higher viscosity that necessitates a higher amount of the green solvent in order to reach that steady state in the fabrication as compared to the other membranes, as compared to pure NMP and DMAC, which are very low viscosity. So this was surprising to us. It was surprising to us that across the board, the green solvents actually came out to be undesirable. When we were talking about just separating out the Dr. Blade only, the impacts were not as significant, though they were higher for the green solvents, but not as significant across the board. When we went to the slot die coating, we saw that just by using slot die coating, all of the impacts were higher. Again, we have to have some sacrificial dope solution to reach steady state, which we don't at the Dr. Blade level. The slot die coater does use power, and it produces a greater amount of waste than we do at the Dr. Blade level. So we are currently analyzing them further, analyzing residuals, and we are preparing a publication that should be coming out fairly soon. But to summarize, as we're approaching the 50 or so minute mark, what we have made here, we have used these green solvents. They are suitable at the bench scale and at the scaled membrane fabrication. We have not looked at all membrane characteristics. We have not looked, for example, at mechanical strength here. We have in publications, but there are some issues with green solvents and mechanical strength. But those are also others that we're focusing on. We're looking, and other researchers are as well. We developed coating windows for the scale up. We determined that by pre-treating a porous support, we were able to successfully cast a membrane on it using the green solvents. And we were able to determine that the pre-treated support using slot tie coating with the green solvents made membranes that have high rejection of PSA and sodium alginate. But we're still working on that life cycle assessment. That life cycle assessment is still showing us that just simply calling them green and calling them better, it's just not looking at the full picture. There are other effects that come into play. There are the viscosity effects. There are the electricity effects. That while Polar Clean is a valorized byproduct, there are other issues associated with it as well because of that viscosity, because of those higher uses. So in summary, it's not easy being green. We are trying. The deeper we go into the green, the more we find potential hurdles, but ultimately the goal is to develop something, to be able to get there. As Susana Nunes once said, what we want is simplicity, scalability, and sustainability, the 3 S's. And that's what we're working on with my group. I now would like to acknowledge all of the people involved in the work. This is my group at NAMS in Alabama. David Liu is the primary graduate student. Again, he just recently defended his dissertation. My collaborator, my long-term collaborator, Tequila Harris from Georgia Tech, her student, Brian June, undergraduates that work with my group and with her group, and our new collaborators, Diana Burns and Isaac from the University of Kentucky, who have been pivotal in helping us understand how to do life cycle assessments. And with that, I thank you very much for spending the last 15 minutes with me discussing the scalability of green solvents for membrane applications. And thank you.